class. This video is to cover the remainder of our notes from our notes today in class. Again, I have to apologize to you guys for not being able to fit in all the things I had planned. I'm going to have to learn, just like you guys, what I can do and can't do in class and definitely use that time more efficiently. So if you're watching this video, thank you so much for bearing with me and watching these remaining steps. So if you have questions on anything that I cover in this video or something's not explained well, by all means, please shoot me an email, come by my office hours, ask whatever questions you have. I'd much rather that your questions get answered than for them not to do so. So it's really easy to shoot me an email. Please just take advantage of it. I get back to you guys really fast. So I have no problems answering questions via email or in person, whatever works for you. So in today's class, we were really doing a lot of things. We were talking about what is a polynomial and getting into adding, subtracting, multiplying, and dividing polynomials. And so we were covering a lot of things. We cover a lot of things in this course, and so that's partly why I ask you guys to do those pre-class videos. So I'm just going to briefly talk about what we already discussed in class, and I'll post all of the filled-in notes on our Canvas site for you. So we talked about monomials and recognizing them, getting an understanding of the coefficient and the degree. And we talked really, the big thing is whether or not something's a polynomial. So you need to look at the power of your variable. So even if you don't have a variable, like C with number 3, that could still be a polynomial if you think of there being a hidden variable raised to the 0 power. The key thing is you can't have fractional powers like you see in problem E, or negative powers. Those both disqualify them from being polynomials. We talked about kind of the general definition of a polynomial and did some examples looking at the leading terms and then also the degrees. And being careful about division, whether our variable is in the denominator, then it excludes it from being a polynomial, but just because there is a fraction, like in G, doesn't mean that it isn't. It could be that, in this case, the division by 2, our variables are still fine. They still have positive powers, so there's no issues there. And then we did a little bit of addition, which is kind of the easiest operation of our 4 basic operations. You're really just adding the like terms. And we talked a little bit about the ordering and that kind of interesting case where you have the 2 variables, how you start in alphabetical order from the highest power of that variable in descending order. So here we have x squared and then the x to the first and then x to the first with the y squared. So we wanted this nice symmetrical x squared being the leading term and y squared being the last term. And it may not be clear right now, and that's okay, why it's ordered that way. When we start doing some factoring problems, it'll make sense why it's ordered that way, because that's the order that makes it easiest to FOIL and factor back out. So that's why it's ordered that way. But even if you didn't have those 3 terms in that same order, it's still the same polynomial. There's nothing wrong with that. So it should be still a correct answer if you type in a different order into my math lab. So now we want to talk about C, which is subtraction. So again, we're looking at those parentheses and determining if they're really needed. On the first set, I mean, we're not doing anything with it at all. There's no multiplication, so we can just get rid of it. But on the second set, we need to be careful. If I just get rid of my parentheses, so I'm going to write this, oops, I don't want my parenthesis there. So I'm going to get rid of my parenthesis, but I want to be careful if it's really meaning the same thing. So there, all I did is I dropped the 2 parentheses. Now, really, I've changed the problem. I don't know if you guys noticed it, but even though I see a negative sign up there and a negative sign down here, by taking away the parentheses, only this 2a to the 4th is getting subtracted. I still want to subtract this entire polynomial, so I want to subtract the 2a and the negative 3. So really what we want to think of this as is a multiplication problem. We're multiplying by a -1 value. So that -1, if I write it there, then we can see it becomes a distribution problem, and we have to distribute that multiplication by a -1 through to all the terms of my second polynomial. So -1 times 2 is the negative 2a to the 4th. -1 times the 2a is going to get me a negative 2a. And then the -1 times the -3 is going to get me a positive 3. So some people think of this instead of distributing like a -1, they think of it as distributing the negative sign or applying the negative sign to all those terms. And you can think of it that way as well. That's okay. But we do need to see that subtraction occurring. So in that case, the parentheses do play an important role. So from there, now we can treat it essentially like an addition problem because I've dealt with that negative sign by distributing it. Now I can combine like terms. So I'm going to go through and identify all my like terms. So I have 3a to the 4th, -2a to the 4th. So we combine those into one grouping as a to the 4th. We add the coefficients. So 3 added with a -2 is 1. You can choose to write the 1 or not. If I left the 1 off, it's still 1a to the 4th, and that's fine. So it's whether you kind of like having the 1 there or not. Then we move to the next highest power of our variable, which is a. So I have 5a and -2a. If I add up the coefficients, 5 minus 2, that's a 3a. And then lastly, we can do our constant term, which is like the a to the 0th term. If you remember, a constant technically has a variable. It's your variable raised to the 0 power. So that's the 0th term or 0th degree term. So here I have -6 combining with a +3. So the -6 added with 3 is a -3. And now I don't have anything left to do. The whole point of these is to simplify, which means you've performed all of the mathematics that you can. What I mean by performing all of the mathematics is doing PEMDAS. If you remember your order of operations, parentheses, exponents, multiplication, division, addition, subtraction, PEMDAS is our order of operations, the order that we perform mathematics. I've done all those things. I've performed all the mathematics that I can, so now it's completely simplified. So we can circle that. That's your final answer. Boom. So that's how you would perform subtraction. Just be very careful to distribute that negative sign through to all of the things you're subtracting. So now we can talk about multiplication. And multiplication, there's a lot of examples in this one because you could have a lot of different cases of how to multiply. It depends upon, in essence, what are the two polynomials that you're multiplying, right? Here we have a binomial multiplying by a trinomial. Truthfully, these are all just distribution problems. If you remember distribution and what that is, you're distributing that multiplication through the addition of other terms. That's really all that we're doing here. Foiling is nothing but a special way of remembering how to distribute. And foiling is when you have a binomial times a binomial. So we'll look at a bunch of different multiplication cases to make sure that we feel comfortable doing all these different types of multiplication. But really, it's all just distribution. So what I'm going to do here, I'm going to actually write this guy out a second time to give myself a little bit more space. You don't really have to do this, but I want to diagram for you that distribution. So distribution here, you could either distribute the 2 terms in the binomial through to the trinomial, or you could do the 3 terms in the trinomial distributing to the binomial. Either way would work as long as we perform the distribution. So I personally prefer taking the binomial and distributing the multiplication to the trinomial. You're literally multiplying all the same thing, so it doesn't really matter, but I kind of like working with a smaller binomial. So I'm going to take my w, which is the first term of my binomial, and I'm going to distribute that multiplication to all 3 items in my trinomial. So what I mean by distribute, I'm going to multiply w by 2w squared. So when I do that multiplication, you're multiplying the like items. So w is going to combine with the w squared. This 2 is going to stay. So you want to be really careful. There's some subtle things that are different between combining like terms, right? When we combine like terms, you're adding the coefficients together. That's not what we're doing here. We're multiplying these items. I'm multiplying the w by the 2w squared. So the 2 is going to stay because this is multiplication, not addition of like terms. And then when I have 1w combining with the 2 w's from the w squared, you're really now combining the powers, right? A power 1 with a power 2 gets you a power 3. So that's the subtle thing that tends to trip people up about algebra, is that we have operations that feel very similar, but how they act is different, right? When we're combining like terms, like in our addition, you're adding up the coefficients. But that's because the operation I'm doing is addition. Here, the operation I'm doing is multiplication. So it's the powers of the variables that are getting added, because the operation is multiplication. So be very careful about this distinction because they feel similar, don't they? But they are different operations, so be careful. So I've done that first bit. Okay, so that one's done. That first distribution. Now I need to distribute my W to the 7W. So again, the coefficients staying the same because of this is multiplication, but the W to the first is combining with or multiplying by the other W. So I have a W to the first multiplying by another W to the first. So you add the 2 powers of 1 and you get a 2. So 7W squared. And then now we go to the last term in our trinomial. So W times 3. Now this one, I have a W on this value on this term, but I don't have a W over here. So the 3 is still going to stay just like before, but that W to the first can't combine with another W, so it just stays as W to the first. Right? So if you notice, it's this exact same trinomial, but all of my W's were 1 more, right? Because I was including 1 more multiple of a W, right? So that one's done. So now I'm going to distribute the -1. Okay, so the -1 is going to distribute all the way through. So -1 times the 2W squared. Now here, be careful. It is still multiplication, but this does not have a variable on it, right? It's just the number -1. So when I multiply the -1, it's going to multiply with my other number, which is the 2. Before, it was a variable, so it multiplied with the variable. So you're multiplying or combining the like variable to variable or number to number, right? So here I'm going to do -1 times the 2. That's -2, and W squared has to stick around. Then I need to distribute through the multiplication -1 times the 7W. So -1 times the 7 gets you -7. And the W to the first is sticking around. And then again, -1 is multiplying by the numerical part, number to number, multiply. -1 times 3 is -3. So again, there's those subtle little differences between adding polynomials and multiplying that we have to be aware of how the algebra is acting. It's really easy to confuse those, so you want to make sure that you clarify that for yourself, right? What's going to happen in those adding problems like before versus the multiplication here. So now this becomes a combining of like terms because I've performed all the multiplication. There's no more parentheses or multiplication happening because it was all performed. So now I can combine like items. So I have W cubed is the highest power of my variable, so we start there, and that's the only one, so it carries down. Then I move to the next highest power of my variable. The next highest power of my variable is W squared. So I have -7 and -2, those add up. The coefficients add up to +5 W squared. And then the next one is W. So I have 3W minus 7W. 3 minus 7 is a -4W. And last but not least, my constant term, the only thing left over is -3, so that carries down. So there is your final answer. 2W cubed plus 5W squared minus 4W minus 3. I've done all the math I can. I've done all of PEMDAS, right? So we're done. And if you notice, when they say simplify, right, that keyword simplify, or you're performing an operation, they really mean PEMDAS. So PEMDAS is that acronym for what we call order of operations, the order that we perform our operations in, right? We do parentheses in terms of grouping. If things are grouped in parentheses and you can perform that operation first, you do it. Then E for exponents, M to multiply, D for to divide, and then add and subtract. So here we didn't have any parentheses, we didn't have any exponents, so we did the multiplication, there was no division, and then we did our addition and subtraction of like items. All right, now a really common thing that we talk about when we multiply a binomial times a binomial is we call it FOILing. FOIL is an American creation. Everybody else in the world just calls it multiplication or distribution, but FOIL is just an acronym to make sure that we properly do that distribution like what we did before. So if you notice, right, this is that same distribution. I took the AX and it got distributed to the first term CX and then the next term D. Then I took the B and I multiplied or distributed it through to CX and D. So if you looked at this, this is just distribution. We gave it this FOIL acronym to help us remember all the 4 parts of that distribution to make sure that we do it correctly. Because sometimes that happens when you have 2 like items like that. It's easy to mistakenly multiply the wrong items again a second time or leave something off. So FOIL helps us remember the process. So what does FOIL mean? F stands for first, so that's our first set of terms getting multiplied. So that's this right here, right? That's F, the AX times the CX. So here, if I wrote that out, the coefficients would multiply by each other, A times C, and X times X would become X squared. So that's how that would work. Then O stands for outer or outside. So that's the second part of our distribution. There's O right there. So AX times D. So A and D are both numerical there because X is the variable. So A times D, and then X would just hang around. And then I stands for inner or inside. So that's the B times the CX. That's the I part. So again, B and C are numerical. So those would multiply, leaving the X as well. And then L stands for the last set of terms, which is B times D. Both are numerical, so those would multiply by each other. So if you notice, that's just distribution. So foiling is just an acronym to help us remember how to distribute a binomial times a binomial. So that's a common language that we use, at least here in the US, is foiling, right? But it's really just multiplying. So here, if we went through and foiled these, right, multiply the first set of terms, 7x times 2x. Remember, you're multiplying the corresponding pieces. So the numerical part, the coefficient of 7, multiplies by the other numerical part, which is 2. 7 times 2 is 14. And we normally perform that multiplication, but just write down the result. If you wanted to, you could write that in between step of like 7 times 2 and x times x. You could write that out, but a lot of times to save space or just to not have quite so much clutter on our page, we do that part in our head and just write down the result. So 7 times 2 gets us 14. X times x. Again, I'm multiplying the variables together. You combine the powers by adding them up. 1 and 1 gets you x squared. So that is the F in FOIL. Now we can do O for outer. So now we do our outer part, 7x times 4. Again, you multiply the numerical pieces. 7 times 4 gets you 28. If you're not sure about those things, that's what your scientific calculator is for. You can type that in if you're not sure what the math side of that would be. And then I have a single x left over. Then I for inner. So we do 3 times 2x. 3 times 2 is 6 with a single x left. And then L for last, 3 times 4 is 12. Now, I foiled it, but here's the thing. I'm not done in my multiplication process because I haven't simplified it all the way down. In every math problem, you want to go all the way, do all the math, follow all of your PEMDAS to the very end until there's no math left for you to do. So I'm combining like terms. I have 14x squared all by himself. Then, let's see, then I have a 28x and a 6x. So those are going to add up. 28 plus 6, 34x. And then our last term is 12. Oops. So just add 12. So there we go. That is our two binomials multiplied out and then simplified down. Okay, so this one would be the same idea. Kind of the only difference between that example A and example B is that we got this negative B. So anytime you see a negative sign, be careful. That's where most people make mistakes. I don't care who you are. You've made a mistake with a negative sign. You got to be careful. Myself included. I know I usually make mistakes with negatives. They're just really easy to miss. So be careful. So anytime I see a negative in my head, I know I'm being more careful with that problem and what that negative is going to do. So 3a times 5a. 3 times 5 gets me the 15. A times a second a gets me a squared. That's my F in FOIL. O for outer. Uh-oh, now I have negative b. Got to be careful. 3a times a negative b. So 3 is going to multiply with the negative 1 to get me a negative 3. And a times b are different variables, so I can't write like a power 2 like I did for a times a. When they're different, you got to write them together, and we normally write them in alphabetical order. So a times b, even though b times a is the same thing, we like to write a times b. Okay, so that was first outer. We got to do inner. So 4 times 5 is 20. And again, I have a times b, so I'm going to write it as a times b in alphabetical order. And then last, be careful, I have 4 times the negative 1, which is negative 4. B times B, I have 2 b's, so that's a b squared. All right, now here we do have some like terms. In this case, my like terms are the negative 3ab and 20ab. Those are the only two items that have the same variables raised to the same powers. So the 15a squared would carry down, and so would the negative 4b squared. Those ab's would add up. 20 combined with the negative 3 is 17ab. And that would be the final answer there. So you could have multiple variables, so just be careful. All right. Oops, let me make sure I did all my multiplications there. Yes, I did. And now there's many, many more that I gave you guys to try. So these, since we've had a chance to look at them, I might go through them a little bit more quickly, but all the same ideas apply. So here I have binomial times binomial. We're going to FOIL. So 5 times 5 is 25. X times x is x squared. Then did outer, so again I have a negative, so I gotta be careful. 3 times 5, negative 15x. And then inner, 3 times 5 this time is positive 15x. And then the last set, 3 times negative 3 is a negative 9. And when I combine up my like terms, something really interesting happens. A negative 15 added with a 15 is 0. And that can very much happen, and that's actually a really good thing. We'll find out later. This is a special factoring process called the difference of perfect squares. But yeah, my x disappears, and so I just am left with 15x squared and a minus 9. So that is possible, that you may not get a perfect trinomial out of this. You might be getting something else if your like terms add up to 0. So that's the result of that one. Now this one, we could fall into a really common algebra mistake, so be careful. One thing I want you guys to be aware of is this power 2 does not distribute into addition or subtraction. So some people like to think, oh, distribute power 2. This is going to be 12a squared minus 5 squared. No. Okay, that's not the same thing. If you're feeling pretty confident about it, I'm going to prove you wrong right now, okay? If I put in a value for a, so let's say a was 2, okay? If you want to try testing something out, this is a good way of doing it, is to let your variable take on a value. So if a was 2, and I replace that, right? This would be 12 times 2 minus 5, all squared. If I follow PEMDAS, what is that? 12 times 2 is 24, take away 5, squared. 24 minus 5 is 19 squared, and that I don't know off the top of my head. I'd have to type that into a calculator, but it's a big number, right? So let's see what that would be. So 19 squared, 361. So this side of my relationship would be 361. Now if these are really equal, I told you that they weren't, but if they were really equal, I should get the same value from this right side. So let's compare the right side. 12a, if I put in a as 2, this would be 12 times 2, then squared, and then minus 5 squared. So what would that be? 12 times 2 is still 24 squared, and minus 5 squared. So 24 squared, again, that's a big number. I don't know it off the top of my head. 24 squared is 576. 5 squared, I know, that's 25. So, I mean, I can type this in for you. 576 minus 25, not 361. This is 551. So what does that mean? There's no way these could be equivalent, right? If distributing that power 2 was correct, I should have gotten the exact same number when I let a be 2, and I didn't. So that's showing that that is not true, that is false, okay? So I just proved it to you guys. Don't do that. You're going to screw stuff up if you do. So if I can't do that, then what should I do? So let me get rid of this, because that's not solving the problem. That was just me going on a rampage and showing you guys not to distribute your power 2 because it's not correct. So what do I do? Well, I want to actually think of this as really like squaring, right? What does squaring mean? Squaring means to multiply something by itself a total of 2 times, right? So if I took this whole thing, 12a minus 5, and I multiplied it by itself, so that I saw 2 of them, right? 1, 2. That's what it means by 12a minus 5 squared. You're going to multiply 12a minus 5 times 12i minus 5. And that now looks like a FOIL problem. And it is. When I FOIL this out, then I will get the correct answer. And we'll see that it's not this 12a squared minus 5 squared, that there's something else in there. So let's do that. So FOIL it. 12 times 12 is 144. A times a gets me in there a squared. Then negative 5 times 12, that's a negative 60a. The inner part also gets me a negative 60a. And then the last negative 5 times negative 5 is a negative times a negative. Negative times negative is positive 25. So when I combine my like items, I have two negative 60s that are going to add up. So I have 144a squared minus 60 plus 60 is 120a plus 25. So notice, I do have some of my parts. The 12a squared is this 144a. The negative 5 squared is the 25. But there's this negative 120a that was not in our previous one, and that's why they weren't equal. When you FOIL, right, it's not just the first and the last terms. You have these outer and inner terms that get involved too. So when you distribute your power 2, you're forgetting the outer and inner terms in FOIL. And that's the problem, okay? So please do not do that, okay? Do not distribute your power 2. It doesn't work, okay? It does not work. What you need to do is write out what it means to square, right? Like for C, I write it out. This is x plus 3y times itself, x plus 3y. And then we FOIL, right? We have to FOIL. So x times x gets me x squared. X times 3y, I have two different variables, so I'm just going to write it out as xy in alphabetical order. Same thing, 3xy. And then the last set of terms, 3 times 3 is 9, and y times y is y squared. So that all comes out to be x squared. We can combine the three xy's together. 3 plus 3 is 6xy plus 9y squared. And there is our final answer. So that's a really common thing. Just be aware of that power 2 on the binomial. Now these last two are like what we saw in that first example. We have a binomial times a trinomial, so you just need to make sure you distribute through all the terms. So if I start with x and distribute through x times x squared is x cubed, because I have a total of 3 x's in there. And then I have negative 3 is going to stay. There's nothing numerical on the x, so the coefficient carries down as is. X times x, there's 2 x's, so x squared. And 9 times 1 more x. So there's my first term all distributed through. Then I can do the 3. So this time around, it's a different circumstance. Before I had a variable combining with other variables. Here I just have the number that's going to affect the coefficient. So 3 times the 1x squared is 3x squared. 3 times negative 3 is negative 9x. 3 times 9 is 27. And we combine like terms, so x cubed carries down. Then I have x squared, but something really neat happens. Do you guys see this? Negative 3x squared added with 3x squared. Negative 3 add 3 is 0. I have 0x squared to write down. I don't write anything down. Then I have a 9x and a negative 9x. 9 minus 9 is 0. I have 0 x's to write down. And then last but not least, I have 27. So this is x cubed plus 27, which seems bizarre, I know, right? Like we had all these terms and I only was left with 2 of them at the end of this multiplication. But that's okay, because this is a special circumstance we're going to find out about later when we factor. This is a special relationship called the sum of perfect cubes. That's what this is. So that's why I had an x cubed and the 27 left. So that can happen, right? That can totally happen. Don't expect the multiplication to necessarily have always a long answer. It may be short. So now let's do the next one, x times x squared. Now I have 3 x's, so that's x cubed. 4x, times x. So the 4 carries down, x and x multiplies to be x squared. And 16 with an x is left. And then the next one, 4 times x squared, you get 4x squared. 4 times 4 gets you 16x. And 4 times 16, that one I don't know off the top of my head. We'll have to multiply that guy out. And I want you guys to realize, too, you can use your calculator for this stuff. You don't necessarily have to know all the multiplications and operations off the top of your head. You'll always have access to a scientific calculator in class. So that's okay. Right? That's totally okay. So now I have x cubed, and last time my x squared canceled out. Here I have 4 and a positive 4, and if you notice, there's no negatives up here, so that makes sense. So in this case, they're going to actually combine, and I'm going to keep my x squared. So 4 plus 4 is 8 x squared. Then we can do 16 plus 16, that's 32x. And then last but not least, 64. So this time around, it was that long polynomial that we're expecting. So sometimes multiplication makes things simpler, or fewer terms. Sometimes it makes more terms. So you can't always say that multiplication is going to give you a long polynomial. That may not be true. So we talked about addition, subtraction, multiplication. Now you got to talk about division. And division in general is going to be the hardest operation of all of our operations. So the good news is division in polynomials works like long division. If you were taught long division when you were taught arithmetic, it works the same, very similar manner. But division definitely takes more work, right? So just kind of be prepared. So if we said that division of polynomials works like long division of numbers, let's remind ourselves how to long divide numbers. So when you want to long divide a number, right, like 14 divided by 4, we do this process. So maybe this is familiar to you, maybe not, but this is called long division. And how it works is you take the numerator. So if I were to, you may see a division written like this, or you may see it written like a fraction, right? So the first number is the numerator at the top, the second number is the bottom. So you always write the numerator inside this little division house. So if I was doing this from scratch, right, I draw my little division house and put the 14 inside, and then we write the 4 on the outside. And then how we long divide is we look at the very first number. So if I look at just the first part of 14, the 1, I want to see if 4 goes into 1 at all. And well, it doesn't. 4 is too big, right? 1 doesn't have any 4s in it, so I don't use anything. You could write a 0, but usually we don't write the 0 there. So I can't use 4. So then I move to look at the next digit, and I include both. So 14, right? How many 4s are there in 14? There's 3 of them, right? And if you weren't sure, you could just count up on your fingers, right? 4 plus 4 more is 8, plus a third set of 4 is 12, and that's the smallest number without exceeding 14 that we can reach. So there's 3 groupings of 4, or 12 in 14. So we write that number above the place value. So we got to the second digit, so there was the 3. These guys multiply. 4 times 3 is 12. We write the result underneath. Let me get rid of this line here. And then you subtract. All right? So 4 minus 2 is 2. 1 minus 1 is 0. Now I would look at what's left over and see if I can continue dividing. But here's the thing. I've reached all my digits. I could keep going by making this a decimal. Right? That's how you find decimal numbers when you divide, by the way, is you keep extending it, make this a 20, and then continue dividing, right? What would be that? There's 4 groupings, there's 16. No, there's 20 perfectly, actually. So this would be 3.5 as a decimal, but we don't have to worry about decimals. You just leave it at the 3, and I can't continue dividing, right? There's not any 4s inside of 2, so then this guy is your remainder. And this guy is what we call the quotient, or the whole number piece that's involved, right? So if I said how many 4s are there in 14, there's 3 groupings of 4 with 2 values left over, right, as a remainder. And how you can check it is if you were to multiply your quotient, this guy's called a dividend, or divisor. If you multiply quotient by divisor, 4 times 3, and then add your remainder, you should get back your original number, which was 14. And we do, right? So we know that this checks out. So let's try some other numbers to make sure that we have this down, and then we'll try it with polynomials. So let's say I did 8 divided by 3. So I draw my division house. The first number goes inside the house. The second number goes outside. And then I'm asking myself, here I only have an 8, how many 3s are there in 8? Well, 3, add 3 more is 6, add 3 more is 9, which goes past 8. So really I only have 2 groupings of 3. So 3 times 2 is 6. I subtract that result, and I have a remainder of 2. 2 is too small to have any 3s inside of it. So this would be 2 is our quotient with a remainder of 2. right? So we often write that 2R2. So there's your quotient, remainder 2. So that one was pretty easy, pretty straightforward. Let's try one that's a little bit more difficult. And actually, I don't want to do 22 divided by 5 because we end up getting kind of a similar situation from what we've seen before. So I'm going to change this actually and make it more interesting. Let's do 97 divided by 2. That's pretty nice. So we set up our division house. The first number, 97, goes inside. 2 goes outside. And now let's play our game. So I'm going to look at just the first digit, not the full 97, just the 9, and see how many 2's there are in 9. So there are 4, so I'm going to write a 4 right above it, groupings of 2, right? 2 times 4 is 8. That's the biggest I can go before exceeding the 9. So 8 minus 9 is 1, and I carry down the 7. So this is why I wanted to show you this example, is so that you could see that first place value being dealt with. Okay, so now I look at the full 17, right? Because I used up all the 9 that I could. Now I move to the next digit to try and look for the values in there. So how many 2's are there inside of 17? There are 8. 2 times 8 is 16. Subtract, and there's 1 left. So I've used up everything I can. There's no more 2's inside the 1. So this would be 48 with a remainder of 1. Right? So that's how our long division with numbers works. Why do we care about long division of numbers? It's to refresh our memory about how this process works, because it's going to work very similar for polynomials. So here's 2 examples for you guys to see how it works for polynomials, and then we'll do some more. So we want to divide f divided by g, right? So to write it in the same way you saw before, that's x squared plus 2x minus 4. Now, if I wrote it the same way they did the numbers with this little division symbol, that's really misleading, because then I'm wondering what really is getting divided, right? Is it just the negative 4 divided by x? It's not really clear. So how they fix that is they either have to use parentheses, right, to show one polynomial divided by another polynomial, or what's a lot more common is to use the fraction bar notation for division. And what you guys are going to see is we're going to use that pretty much exclusively in this class, because this sort of division, it's misleading, and if you don't draw your division symbol really good, it's going to look like subtraction. It's just too easy to mistake, so we prefer that long fraction bar. So how would we work that? Well, we would draw our division house. We write the x squared plus 2x minus 4 inside the house, and then the bottom goes outside x minus 1. So I said this was really similar to long division numbers, and that's true. There are a lot of similarities. The first thing we're going to look at is, again, I'm only looking at like the first place value, so to speak, which is x squared. I'm going to just focus on x squared, and I'm also going to just look at the first term here, which is x. So again, I'm seeing how many x's are there in an x squared, but instead of it being numerical, it's algebraic, right? So really what I kind of ask myself is, how do I make this x? I have to multiply by something, right? We multiply the number on top by the number out in front. That's the idea. I want to multiply and get this same result, which is x squared. And in this case, it's a little bit simpler. Instead of getting the next closest number that goes into it, you want that exact same expression. So I want to turn in x to be exactly x squared. How do I do that? I multiply by x. So x times x gets me that x squared. All right, and then we'll subtract that later on. But here's the thing. That worked for the first term, but we got this negative 1 as well that we got to deal with. So that's the one little thing that is a little bit different in this process, is you focus on the first term to find the multiplier, but then you have to continue multiplying. Right? So I did x times x got me x squared. Now I got to multiply the negative 1. X times negative 1 is negative x. And most people are okay with that process. Where they tend to make mistakes is the next step, which is subtraction, right? We did our multiplication, and then we subtract the result of that multiplication. But unlike a number, I have multiple terms here. So I have to do x squared minus x squared, but I also have to do 2x minus negative x. And because of that minus negative, there's change of signs, which can be confusing. So one trick I'm going to show you guys is when I do the subtraction step, I actually change the signs of my whole result before I add down the column to make it easier. But just remember that you're doing that double subtraction. So 2x minus negative x turns into 2x plus x. 2x plus x is that 3x that we see. And then to make things easier, we just carry down the next digit, kind of like we carry down the next digit of the number. We carry down the next place. So now I restart the process. Right, I'm going to restart the process. So I'm going to look at just the 3x. Right? So I'm fixating on this 3x and the x. I want to multiply I want to multiply x by something to get it to match exactly 3x. So what is that multiplier? It's a positive 3. 3 times x is 3x. Matches, beautiful. But then I got to remember to multiply to the negative 1. 3 times negative 1 is negative 3. So remember that process, right? We're trying to get this first leading term to multiply by something to match the first leading term of our result. Then, from here, again, we're going to subtract the result and be careful about that subtraction, right? Because of the change of sign. So 3x minus 3x is 0. Don't have to write anything. Negative 4 minus negative 3 turns into negative 4 plus 3. And that's where the negative 1 comes from. And I can't continue dividing, right? Because I can't multiply x by something and get a negative 1. It just doesn't work. So that's why we know that we're done. So then the quotient part would be x plus 3. And how we write our remainder is a little bit different, right? I don't want to write x plus 3 r negative 1, right? That's not very helpful. So what we do instead is we write the quotient part, and then we write plus whatever your remainder is, and then you write it over the original denominator, which is x minus 1. It's kind of like writing a mixed fraction. It's kind of the same idea. Like if I went back over here, I could have also written this as 48 and 1/2, right? Because the remainder was 1 and I was dividing by 2. Same idea, right? This guy was 2 and 2/3. Same idea. We're writing it as the whole part and then the fractional part, right? So that would be the result of our division. The next one is very, very similar. Again, we're looking at that first term on each of these and seeing what do I need to multiply by x to get it to match x squared. It's that x. Then you got to complete the multiplication with negative 4. Be careful in subtracting the results, and then move. Here I have an x left over. What do I multiply x by to get it to match? Well, nothing, but I can't write nothing. It's technically a 1. So 1 times the x gets you the x. Then you do 1 times negative 4 gets you negative 4, subtracts. And this one's interesting because the remainder is 0, which is actually pretty neat. What that means is that when I divide x squared minus 4x minus 4 by x minus 4, they divide what we call evenly, right? There's no remainder left over. So how we would write our answer then is it's just x plus 1, right? So x squared minus 3x minus 4 divided by x minus 4, that divides evenly to just x minus 1. And that can happen with numbers as well, right? 12 divided by 3 divides evenly to just 4 without a remainder. This is similar to that, right? It divides evenly, and that can happen. Okay, so let's try some a little bit more complicated and make sure we have this division thing down. So again, you write your division house. You put the top, whatever the numerator is, you write it inside the house. And then the bottom goes outside, 2x plus 3. And then we play this leading term matching game. So I have 4x squared and a 2x. So I want to multiply something by this 2x so it matches the 4x squared. Let's start with just the numbers. How do I get 2 to become a 4? I need to multiply it by 2. Oops, sorry. So 2 times 2 is 4. How do I get x to turn into an x squared? Well, I need to multiply it by second x. So x times x is x squared. So there it matches. And if you notice, I wrote the 2x in this column because it's kind of like place value. This first column is anything that has an x squared. The second column is anything that has an x. And then the last column is anything that's constant. I mean, if you shifted it over, it's not going to be a huge deal, but we kind of treat each term like a place value. But I'm not done. I only multiplied the first 2x times 2x. I got to multiply 2x times 3. So 2 times 3 is 6, and we got an x. Now comes the crucial step, subtraction. Okay, so I need to subtract this whole term. Now if I wrote just minus, I only subtracted the 4x squared. So what I do is I distribute that multiplication. It's minus 4x squared. This will turn into a minus 6x. Okay, so I find it's helpful to just completely change the signs of all the things you're subtracting, then add them up. So 4x squared minus 4. 4 minus 4 gets you 0x squared, so I don't have to write anything. Negative 4x minus 6x is negative 10x, and then carry down negative 9. So I think it's a little bit easier to write the results that way. So that's why I suggest distributing the negative through. So now we start the game again. Negative 10x and 2x. So to make 2 into a negative 10, I need to multiply by negative 5. And this has an x, and this has an x, so I don't need any additional x's. So negative 5 times the 2 is negative 10 with an x. Negative 5 times 3 is negative 15. And now we do that subtraction, change of sign. So now if I subtracted, right, if I did subtraction out here, I have minus minus. So what I do when I distribute that multiplication is I change the signs, right? That goes positive, that goes positive. So I've technically done subtraction by minusing negatives, and those became pluses. So 10x plus 10x, that's 0x, which is what we want, right? You always want that first term to go to 0. If it isn't, we're not doing our division correctly. And then negative 9 add 15 is a positive 6. And I can't keep going because this has an x and this doesn't. So then how would I write my answer? The answer from this division is I get the whole part, which is 2x minus 5, and then I add the remainder part, which is 6 of the original denominator, 2x plus 3. So there it is. In my math lab, they may ask you to type in your answers a little bit differently. It may ask for the quotient and remainder. So this would be the quotient part that you would type in, and this would be the remainder part that you type in. But if we wanted to write it as one algebraic statement, that's that first part up there. Okay? And last but not least, set it up for our last one. Now, one thing I want to point out to you guys is that this polynomial is not in standard order. And you might notice that as you were trying to write it out. I have 2b to the 4th, but then 7's in front. And part of the reason why we write it in that decreasing power or decreasing degree of our polynomial is that it helps in things like this, right? If I wrote out 7 plus 2b to the 4th plus 5b squared, it's a lot harder to perform my division, and honestly, we'd probably screw it up. So you want to reorder this properly. So I'm going to rewrite the top of this so it fits our standard form, right? So highest power b is to the 4th, then b squared, then the 7, and then b squared plus 2. So yeah, if they do that to you, reorder it, and you're gonna be a lot better for it. The other thing is we do have some terms that are not there because technically the coefficients are 0, but I don't have a b cubed and I don't have a b. So you could just write it out as b to the 4th, 5b squared, and 7. Usually what I do is I leave myself a little bit of a space because sometimes when we're dividing, I don't think it's going to be the case here because we're dividing by also something that has a missing term, right? The b squared plus 2 is missing a b, so I don't think it'll matter. But sometimes what ends up happening is you end up creating some of those missing terms as you go through the division process. So my suggestion is leave yourself like a little bit of a space for if there was a cube, right? It would follow that place value system. So b to the 4th, there's no b cubed, plus 5b squared, there's no b, and plus 7. So just leave yourself those kind of like little blank spaces in case you need them. You may not. In fact, in this one, we will not. I can pretty much tell you right now. But that could be the case. So just on the inside part. On the outside part, it doesn't matter. All right, so let's play our game. I want to get my b squared to match this 2b to the 4th. So how do I create the 2? I need to multiply by 2. How do I turn b squared into b to the 4th? I need another b squared. So though we'd write that above the b squared column and perform our multiplication. 2b squared times 2b squared. Oops, sorry. 2b squared times an additional b squared is 2b to the 4th. Then I have to continue with this other 2. So 2 times 2 is 4 with the b squared. And now we subtract. right? So remember, subtraction distributes through. I'm just going to make them both minuses. So the first term goes to 0, which it absolutely should. If it doesn't, we're doing something wrong. 5b squared minus 4 is 1b squared. I'm going to carry down the 7. All right, so now we play that game again. I want my b squared to match this 1b squared. Well, here's the funny thing. They already match. But remember what we did last time. When they already match, then by default the multiplier is a 1. So don't forget that. Your multiplier is a 1. So 1 times b squared is that 1b squared. 1 times 2 is 2. And subtract. So subtract, subtract. We get 0, which is what we want for that first term. And 7 minus 2 is 5. So what would be our answer in this one if we wanted to write it out? So remember, your quotient is this 2b squared plus 1. Remainder is 5. Or you would write it out 2b squared plus 1 plus 5 over our original denominator, b squared plus 2. All right, so there it is. I hope that helped you all in better understanding the polynomials and the 4 operations. If you have any questions, please feel free to email me or use my Math Lab. My Math Lab has a lot of resources, so as you're working through the problems, sometimes clicking on the Help Me Solve This or view an example sometimes really helps. But please do not hesitate to come talk to me if you have any questions.